Now, I want to demonstrate how the DC motor works. I'm talking about the simple DC motor versus mine. So this is the DC motor, as you can tell. This is called a loop, and it has to rotate exactly 180 degrees, and then the current is reversed with these brushes from negative to positive. So the attraction becomes repulsion, and repulsion becomes attraction. Well, of course, nowadays it's so different because as you can tell on this DC motor, which I removed this from the Toyota, and this has 12 poles. So in other words, instead of rotating 180 degrees, this is rotating 30 degrees, and then it's so powerful. Nowadays, they don't make this anymore. It's just to demonstrate how the DC motor works. But no matter what, always you have to reverse the flow of current. And as you can see, this loop is going through or experiencing the Lorentz forces also, but it has to be in a magnetic field. And this is the most simple motor ever built, and these are called the commutators. In other words, it's reversing the flow of current from negative to positive. And nowadays they make like this with 12 poles, and some of them are so powerful, like this one. This one has 22 poles. As you can tell, it's so powerful. So in fact, every 16.3 degrees this is changing the poles. Well, of course, mine is different. The way I make my electric motor is entirely different. See, the simple one is exactly like a loop, and then we can consider this left and the right loop, and each one is independent, has nothing to do to the other one. So we don't have to change or reverse the flow of current in order to rotate this 180 degrees to 360 degrees. Each one is rotating like this in a magnetic field, and it's so powerful it continues 360 degrees. So is that one. So I have the drawing over here. You can see I even did it with a single wire. Single wire was almost 2 grams, and then when I shorted this wire, the deflection was so powerful, it rotated so many times. And it's impossible to do a single wire in ordinary DC motors, because if you don't change the flow of current after 180 degrees, the normal DC motor will stop. Well, of course, I will demonstrate everything, and then I will explain exactly how the Lorentz force work. As you can see, if I extend my hand like this, my palm is the magnetic field, and my thumb is showing the current, and the Lorentz force is exactly perpendicular to the current and the velocity and the magnetic field. One of the most important things in the history of science was the cathode ray tool. Before the new TVs were invented, this was so important. This is the way J.J. Thomson in England, he discovered the electrons. And that was so important in the history of science, because from then on we knew that if we have a vacuum tube like this, like a cathode ray tube, we can steer electrons from left to right, right to down, up and down, and then this is the screen. We can write down the screens, anything we want, and from then on, everything was changed. As you can see, this is the cathode ray tube, the old one, and this is the cathode ray tube. Electrons are emitted from here all the way to the screen, but in between this neck, you can have deflection coils. They're horizontal and vertical, so they can deflect the beam of electrons the way we want it, and then it is projected on a spring which is phosphorus, and then we can see everything is illuminated here. Well, of course, I have to show you exactly how the Michael Faraday's first electric motor works. And this is Michael Faraday's electric motor, and as you can see, there was a single wire rotating around the round magnet. Well, of course, there was a ball like this, and then those days he did not use electrolyte, he used mercury, and then when this was connected to positive and this to negative, and then this wire was rotating around this round magnet. Well, of course, I would say probably the RPM was almost 200 RPMs, but nowadays we never use mercury, we can use even electrolyte on this. So as soon as you connect the circuit, this is going to go round, and depending upon the polarity, this can go clockwise or counterclockwise. And this is the Lorentz Force. As you can tell, I start with a simple one, and this is exactly the way this principle is used in this multimeter. If you see that indicator or pointer, inside is a small coil, and we have south and north poles, and then as soon as I have a current like 2 volts, 5 volts, whatever, it depending upon the voltage, so this coil is energized and deflected. As you can see, we can measure the voltage, we can measure the current, everything this. And this is another thing which is so important. This is a speaker. As you can see, there's a coil inside, and then as we energize this speaker, depending upon the polarity, this can be pulled in or pulled out, and then it works. This is an old multimeter. I removed it. As you can see, there's a pointer here, and then as soon as you apply the current, this coil is deflected. But you know, in order to end the confusion, always I start from the negative to positive. Or in other words, I follow the flow of electrons, which is from negative to the positive. And now I'm going to show you how this works. My battery is 12 volts, 1 amp, and it's a real good battery. And then I show you, if I start with a minus on this side and plus on this side, exactly like this multimeter, it's going to go conventional clockwise. But if I do the otherwise, this indicator is going to go backward, or in other words, this is going to be plus and minus. So as you can see, as soon as I short this, look, did you see that? Well, the reason why it's not going 360, because first of all I can't find that, and then if I change flow of current, you see it's going to go the other way. Did you see? It's going backward. And then I'm going to show my simple electric motors. And this is just a single wire. And the reason why I have half a loop here is in order to increase the moment of inertia, because that half loop is so thin, it's only 2 grams, it's not going to rotate. Well, of course, it's a challenge to work this because it is so thin and it doesn't even have a lot of mass to rotate. But I will give it a shot. Let's see if it's going to work. So you can see, as I connect this, because this is in a magnetic field, that one is an S magnet and this one is an N magnet. Let's see if we can move this. Hopefully you can see it. Did you see? With a single touch, it goes at least 6 or 7 RPMs. But this is the better one, and as you can see, the wires are much thicker and stronger. And in fact, when I measure this with my Gauss meter, this is the Gauss meter. Let me turn that on, you can see. The precision on this Gauss meter is amazing. I would say it's 100%. A single wire like this, a single wire, not even wound or spiral or anything, the single wire can have almost 20 Gauss. It depends upon how thick the wire is and how much current is flowing. So this is my single motor. As you can see, it has 2 loops, and each loop is working independently. It has nothing to do left to the right or right to the left. We put it this way so you can see the rotation. Did you see the rotation? This goes almost 200 RPM, almost. Well, of course, I have another one. This is thin wire. This one has less RPM because the flow of current is not as good as the other one. Let me see. No, this is not the one. This is the one. This is another one. So every time one loop, half a loop, is deflected and the other one takes over. In other words, see, you can see I'm not changing the flow of current. It's from minus to plus, but what it does, it is changing itself. I turn this off. Now I will explain exactly how my electric motor works. So, I work PVCs like this. As you can tell, it's a PVC. Almost everything in my experiment except there's magnets and ball bearings, or even the ball bearings are recycled. I had to buy the PVC and the magnets only. As you can see, I use 2 types of PVCs. One of them is 4.5 centimeters and the other one is 3.5 centimeters. And I have like 2 coils on each side and 4 coils also. Let me show you the 4 coils on each side. Few minutes ago, I thought, I said the breakthrough in science. As soon as you see, there's only one connection for these 2 coils. So one is clockwise, and the other one is counterclockwise. And this is really breakthrough in science. As soon as I energize the first coil, the first one is becoming north and the second one simultaneously becomes south. So this interacts with the magnetic field on each side. So in other words, I don't have to wait for this to rotate to become north and south. So is this one. See, clockwise and counterclockwise. Well, of course, I should show you in a minute how they work. I had to take one apart so you can see exactly how this works. Some of my coils are vertical, like a rectangle. Some of them are round like this. But in order to increase the efficiency, I had to put 2 coils on one side and 2 coils. But as you can see, the first coil is always clockwise to respect to the flow of current from negative to positive. And the second coil is counterclockwise. I will explain. In laws of physics is so important. The reason why the second one is going or becoming south instead of north, because in physics we have dipoles. In 1 millimeter thin wire we got 1 billion dipoles. So in other words, dipoles, I would say, is like a magnet. So the reason why it is changing, because this is changing flow of current from clockwise to counterclockwise, and the orientation of dipoles is changed or reversed with respect to the flow of current. And as you can see, I removed this from the photocopy machines. Well, of course, these are from the printers. I used almost everything. I didn't even buy the wires. As you can see, these are good wires from the alternators, from the automotive, all household items. As you can see, so every time this rotates, as you can see, these are the connectors. And then when it rotates 180 degrees, and then here comes another 180 degrees. Which unfortunately, this is not the way I want it, because I don't have the factory, I don't have the tools. I won't be able to do it like the other ones, like this, like 8 poles. But overall, the RPM is so good, I'm happy with it. And as you can see, there's one magnet south on this side and north on this side. And then when you apply the current, you don't have to change the flow of current. It stays the same. But see, this is rotating according to the polarity, if you have negative and positive. This was so important. And as you recall, I talked about it, I mentioned the breakthrough in science. So you can see this coil is 300 Gauss when I measure with my Gauss meter. And that one is also 300 Gauss, is north. As soon as I flip this, see what happened? This becomes north, south. But as you can see, the flow of current is not changed. It's from minus to plus. But the advantage of this new concept is I don't have to do, probably in a millisecond, this one is energized, so is that one. Because imagine, that is almost like 8 or 10 meters higher. It's not that long. Even though the current is not flowing that, the speed of current is not that much, but it doesn't matter. So this becomes north and south. And the advantage is, this is interacting in a magnetic field, which one of them is south, one of them is north. Well, I'm going to show you one, and then show you exactly how this Gauss meter works. See, I turn this on, and then I bring it to 0, see? And then this probe is so important. It's called Hall effect, and it's so sensitive. So as soon as I put this on this magnet, this coil, it shows. And normally, in a center, always we have more magnetic field, and it's just going around, and on the edges we have less. Okay, so I turn this on so you can see. See, it was showing 300. It was showing. See, it was showing 300 Gauss, or 250 or 300. And in fact, I made so many. Some of them are thick wires like this, but the best I made was this one, which was so good. I worked many months on this, and as you can see, it's not one layer. There are 4 layers of wires, and this is the wire. I removed it from the alternator of a automobile, and that is 1000 Gauss. So if I have like 4 coils wrapped around like this, you will have 2000 Gauss, which is so good. And then I'll show you one of them so you can see. That's minus to plus. And then, as I said, concentration on the center is always much more. So as you can see, how important it is for these coils, how they're made. And unfortunately, my hands are tied. Like this small coils, you can see how small they are. Each one has 700 Gauss. There is no way I can do this because I removed this from the hard drive of a computer, and they have 700 Gauss. And imagine if I put 10 of this, it's going to be 7,000. That electric motor is going to be so good. Probably it's going to go to 20,000 RPM. But unfortunately, I don't have it. But this is the best one I use, these two. And they're 1,000 Gauss. And like I said, I'm happy with this, and it's okay. And I show more. In my electric motors, I have to use straight magnets. But unfortunately, I could not find round magnets. See, you will never ever see a straight magnet in any electric motors. But see, they're round like this, and I can show you. See, even in alternating current, they're round like this. Well, of course, I removed the winding. You can see they're round like this. And there is no way you can see, but you know, I had no choice. But the reason why I say this, because why? This is rotating, as you can see, only in the center. As you can see, when it rotates, it doesn't matter how close it is, but it is not exactly the way the curvature of this magnet is. When this rotates, the Lorentz forces are so good in the center, as it goes past that point, it's not that strong. But if I had a magnet like this, as you can see, or a little bit larger, it would go around it. It could have been much better, but unfortunately I couldn't find a magnet like that. And this one is from the starter of the automobile. You can see this is perfect. I show you. See, when you rotate that almost 130 degrees or 120 degrees, you can have the Lorentz forces. The reason why the Lorentz force is supposed to be perpendicular. But in my magnet, if it's straight, it's only the center part. Well, anyway, I had no choice because I couldn't find a round magnet anyway. And one more thing I did, magnetic field is amazing. Sometimes you think about the copper and silver, they can conduct electricity well, so good. And this is the thick sheet of metal, or I would say iron or steel. If I have this magnet, I show you, this might be 1,000 Gauss. Let me put it. So this is showing 500. This is showing 875. But as soon as I put this underneath, so what it does, the flux line or the line of forces which Michael Faraday used to say, they are concentrated upward. In other words, they are not scattered. And then you can see the magnetic field is improved from 750 to 920. I discovered that this is so important. Well, of course, I couldn't find the thicker one. If I had like a 3 millimeters iron, that could enhance this almost like 30%. But this is enhancing 20-25%, which is not bad for my purpose. And as you can see in my electric motors, I use them a lot. This is another one. I use it in colored wire, so you can see there's only 2 connectors, and the way the orientation starts is from negative to positive. And then, as I said, these are clockwise, both of them, and the other one is counterclockwise, but they are using the same current. It's not changing. And as it rotates, everything changes. It takes over. Well, I could not do more than 4 coils because it was impossible. I couldn't. I don't have the tools. I'm not a factory. But you know, because I have experience all my life, I could do this anyway. I'll put this Gauss meter away. And this was so important in my science experiment. This is a tachometer, and it can go to 99,000 RPM, which is more than enough. But the reason why this is easy to work with, because if I have, let me show you. If I have a reflective marks like this, the white shining reflective mark, this is reflected, and then it can show the RPM. So I show you. And as I mentioned, my electric motors start from 2,800, but in last few months, I'm retired. I improved it to 7,000 RPM, which is amazing. It's more than 200% or even more. So, as you can see, this is the same thing. And unfortunately, I couldn't find a copper, real good copper, because they're so thick or so thin. I had to use brass, which is not a big deal anyway. So, these are the connectors. So, as you can see, one coil is energized, and then deflected, and the other coil takes over, and on and on and on. And this is so good. This coil has 1,200 Gauss, which is unbelievable. I mean, in my purpose, this is the best. I show you now.